Okay, as I have mentioned, no, it is not just only with methyl shift or methanide shift that we can have a shift to produce a more stable 3-degree carbocation, but it is also possible with a hydride shift, no, to produce a 3-degree carbocation. So you have to take note whenever you have a 2-degree carbocation, there is always the possibility that a 3-degree carbocation can be made. And because here you've seen that this is only feasible when we have a carbocation, so this kind of rearrangement occurs only in the E1 mechanism. So in biological system, no, rearrangement of carbocations can also lead to a change in ring size. For example, you have here your alcohol, okay, and you can leave this one, the OH can live, of course, in the presence of the acid. Always have to remember how that the hydroxide cannot live by itself. It always has to be protonated first with the acid to live as an H2O, and you get your carbocation. So here, once you get your carbocation here, this is a 2-degree carbocation. In this case, it was possible to have a rearrangement, no, where we involve the ring to have this. So what happened when the ring is involved? You notice that what is adjacent here, adjacent to the positive carbon here, is a 1,2 tetracarbon. Okay, it's a tetracarbon. It's bonded to 4 different alkyl groups, H3, this one, and this. Okay, so it shifts here. Okay, it breaks the ring here and shifts to here. So you'll get 1, 2, 3, 4, 5, 6 atoms. So there is a shift you have here, copy lang na, and you shift, break this bond, and use the electron, the covalent bond, or the electrons used in this covalent bond to form a bond here. You get this. And the carbocation is now formed here because carbocation here is already satisfied, or the charge or the octatle is already satisfied here by forming the bond here. So since si kani ang gikuhaan, no, to form a bond here, when the shift occurs, katong carbon that is involved in the shift will carry itself the electrons in the bond, so that the one that's left behind will have the positive charge. Okay, so this becomes the positive carbocation, and this is actually a 3-degree carbocation. So since we involve 1, 2, 3, 4, 5, 6 carbon atoms, we can actually rearrange this one to look like this, no? Para mas nindot tan-awon with the hexagonal shape for a cycloalkane. Okay, and you have a positive charge on this carbon here, which is a 3-degree carbocation. And once you have this, the base, hypothetical base, can now abstract the beta proton, and you will have to look that there are 2 kinds of proton that is involved. You can abstract katong left and right. You always have to look on the left and right of the carbocation on its proton, right? So you can abstract the proton here. This is a beta carbon. This is also a beta carbon. So the beta proton can be abstracted with the base. So if this is the proton that can be abstracted, you get your double bond here. The base abstract the proton, the bond between the carbon and the hydrogen will go into as a double bond. Okay, mawala na ang positive charge. Nga naman, because of course, carbon satisfying ng the octet. Okay, so you have now the alkene. If the base abstract the outer proton here, you get your alkene na adiriya, right? But what you will get in that is a tri-substituted alkene. But of course, what you've learned that in this case, this is a tetra-substituted alkene. This is the more stable one. So what is shown here is only the more stable one, but you can also have a side product with another alkene. Okay. I mean, it's possible to have a side product, but this one is the major product, of course, because this is a more, this is the tetra-substituted alkene. Okay, let's have a problem. Explain why the major product of the dehydration above is 1,2-cyclo This is, I have already mentioned this one. Why is the major product this? Okay, you've noticed this is our major product. And not why is our major product this one? 1,2-dimethyl cyclohexane and not 2,3-dimethyl cyclo 1 cyclohexane. No? Because I have already mentioned that you also have a beta hydrogen. Dili maklaro, tama? But you just have to imagine, no? Kani? Or do I need to write it? Kailangan pa ba na akong isulat? Okay, once you have your hydrogen, of course. Emphasize na natin si hydrogen here. Napaka-isa ka hydrogen, diri right? So your base can also obstruct. So the base can also obstruct that one, the proton, and when it's obstruct this proton, the electrons from this bond will be used to form a double bond. So what you will get actually is, internet is stable. You'll have a double bond here, and of course your CH3, and you have your, of course, hydrogen and CH3. Okay, so but this one is the major product, and this one is the minor. And why is that? Because this one is tetra. You have 1, 2, 3, 4 tetra substituted alkene, and this one is only, you have 1, 2, 3 tri substituted alkene. Okay, and for that reason it follows the Zaitsev, wrong spelling, Zaitsev rule. Spelling. Okay, ZDI, sorry. It follows the Zaitsev rule. Okay, so that's the reason. Let's go back to the problem. Why this is the one that's only shown here, but as I've mentioned, there is a side product. You can have this one. It's a minor product. Let's say side product, it's a minor product. Okay. It's very simple. And then let's proceed. I think you can answer this one. The acid catalyzed, another problem. Acid catalyzed dehydration of pentyl yields 2-methylbutene is a major product, outline and mechanism. By the way, since we have already have the E1, E2, no, and we have the SN1, SN2, I expect you to know the mechanism behind all this kind of problems. So part of the exam, I already have to tell you that the mechanism will always be involved. I will always have to ask for the mechanism. When you can never be wrong if you know the mechanism. Okay, if, for example, you get confused, like how would it happen? Would it be E1, E2, and something like that? You always have to remember always the mechanism. Always follow where the electrons go, where the bonds converted, where the electrons go to form a bond, or bond breaking to form another bond, something like that. With the mechanism, you can never go wrong, and you can always predict on the product. Okay, so part of the exam on our midterm, which actually between April 7 to 13, I'm not wrong, so it will be our midterm exam. The mechanism, I will have to, that will come out on the exam, definitely. Okay. So next question, acid catalyzed. By the way, when you are given like something acid catalyzed dehydration of neopentyl alcohol, like you have the structure, even without the structure, you're just given the name. It's always important to draw on the structure. Pag dili klaro, okay, for example, dili klaro, which hydrogen will be abstracted or not. No? So you have to show on the hydrogen para maklaro ninyo asa ang ma-abstract, asa ang mo-form og bond with a base. So para klaro niyo, you have to emphasize, for example, here, hydrogen has to be emphasized para makita nato that this is the hydrogen or the proton that is to be abstracted by the base, and that you can see where the electrons from this bond sa hydrogen will go. Okay, in the same way that you have drawn this one, no, dili klaro asa man to siya. So you have to draw on the hydrogen para klaro si base with its electrons here, maklaro siya as a dapit. Okay, so you have, okay, dapat nagikan sa electron ang arrow na to. Okay, so dapat i-draw na to para maklaro na to asa ang bond. Okay, so we do reactions. So you can proceed with this reaction. It's easy. You have this one, so you have a ring. You have this ring here. So for example, you don't see the expected alkene or product. Then whenever you have the reaction and it's not the expected product, then there will always be the possibility of the methyl or the hydride shift. Okay, for example, this case here, when the compound called isoburnio 7.18, the product reactions a compound called and not bornylene, not this one. Okay, as one might expect, using models to assist you write a step-by-step mechanism. This one is good for you to practice. No, so here we should expect there is two kind of there is no beta hydrogen here. No, it's fully carbon-carbon, but you only have beta hydrogen here. If this is a beta hydrogen here, this is our living group, no? Can form a double bond dapat diri, right? But what happened? You have in sulfuric acid, it's very, very strong acid. So it should be an E1 mechanism. So you get a carbocation. So you don't get this one instead, no? But theoretically, you should get this one. But instead, you get this one here. So what happens? Okay, so you will have to obtain a carbocation with a shift. So where does the shift go? Okay, I will have this one. Reminds me, this one will be your problem set. Some good example. Okay. So let's go to the acid catalyzed dehydration of 2-methyl 1-butanol. This one you have to draw gives 2-methyl 2-butene as the major product. Right? A plausible mechanism. Okay. You have another problem set. So I'll post your problem set online. So rearrangement after dehydration of primary alcohol. So what we had so far in the example is a 2-degree alcohol, right? You had a 2-degree alcohol here. So let's go to a rearrangement after dehydration of a primary alcohol. So rearrangement also accompanies the dehydration of primary alcohol. So not just 2-degree alcohol. So since a primary carbocation is unlikely to be formed during the hydration of a primary alcohol, the 1-degree carbocation is very, very unstable. In fact, you've learned the differences between SN2, SN1, E1, and E2, no? That the kind of substrate, which one is favored or not. Okay. The alkene is produced, we've learned that primary carbocation is unlikely. It's very hard to form the carbocation. It's very unstable during the dehydration of the primary alcohol. In fact, when we do dehydration of the primary alcohol, we always have to do that in extreme conditions. Very, very strong acid at a very high temperature. So the alkene that is reduced initially from primary alcohol arises by an E2 mechanism. So whenever we have an whenever we have a primary alcohol, it follows the E2 mechanism. Okay, so first step of the mechanism for the dehydration of alcohol, the first step you have here, primary alcohol, and you have your beta hydrogen here. Okay, so what happens is you have your general reaction, you form an alkene, and you have the rest. So the first step, formation of rearranged alkene during the dehydration of alcohol. Okay, so you produce an initial alkene. Once you produce your initial alkene, so the alkene can actually form carbocation, no? So the primary alcohol initially undergoes an acid catalyzed dehydration by an E2 mechanism. Okay, so not an E1 but an E2. First step is the formation of the carbocation by an E2 mechanism. So you will have your electrons from the double bond will be used as a base to abstract the proton, and the A or the conjugate base of the acid will bear itself the electron. So what happens is you'll first form a carbocation, okay, but it is not by abstracting, no, with the one that we usually have to do, we have to abstract, no, but this one again is we use the electrons from the pi electrons. This will become our base. To abstract the proton, we get our carbocation. Of course, when you are to choose which carbocation will be formed, you always have to choose a carbocation that will be more stable. For example, here, when you do your carbocation, this is an R, you can always have your positive here, or you can have your hydrogen, you can have your positive here. Okay, so you can form your hydrogen, your hydrogen here, and you get your carbocation here, or you can form your carbon hydrogen, and you get your positive here. Do you get what I mean? So there are two ways for which you can get your bond. No, first one is when the carbon from the when the electrons from the double bond will form a bond with proton, you have two options actually. No, the bond will form because there are two carbons from the pi electron. The carbon, the electron, the bond will be formed by this carbon here. Wala din niya. If you get a carbon, hydrogen, should be a red, and you get your positive here. No, but that will be a primary carbocation. Or you get your bond here, and you get your tertiary carbocation. So in the formation of the carbocation here, you always have to choose your carbocation that is more stable. So here we have formed a more stable carbocation than the other one. Okay, and then the pi electrons of the initial alkene can then be used to form a bond with the proton. This is the one that they have mentioned at the terminal carbon, forming a secondary or tertiary carbocation. Again, as I have mentioned, no, should I? Okay, let's eliminate this. I didn't. Okay, so you have here, okay, kanina day. So you have here your, so the first step. Tama, this is the, so you have in here, you have two options, no? First one is you can form a bond with this. The pi electrons from this one can be formed a bond with this first carbon here. You have here carbon, hydrogen, and then you get your carbocation. The second one is if you have, I use blue. The second one is if you form a bond with this one, you get your CR, no, RRH. And then this is the third carbon. You get your C, the red but not pink. Red na lang, you use the red with the hydrogen here. And then you get the R. And you have your C, H, H, okay? And of course, this is where you get your positive. Your positive carbocation. Your carbocation is here. So between this, which is a primary carbocation, maklaro akong green, and this one, which is a secondary carbocation, okay, which one will you choose? Now you always have to choose the more stable secondary or tertiary carbocation. Sorry, this is actually a tertiary carbocation. You have an R here. So this is a tertiary carbocation. So you always have to favor the more stable or the most stable carbocation. Most stable is a 3 degree. Okay, so what you have here, so this one is not formed, but you only form this. So once you have that, this carbocation here, okay, you can already predict your which beta hydrogen will the base obstruct. So here you have your two carbocation, you have your tertiary carbocation rather, and you have two beta hydrogens, the red and the green. So your base can obstruct the green or the red. So if it obstruct the green here, you get your alkene. If it obstruct the red here, you get actually your di-substituted alkene, no? But of course, this one is the more substituted alkene, so this will be your final product, or your major product will be your final product, okay? A different beta hydrogen can be removed in the carbocation you have here so as to form more highly substituted alkene than the initial alkene, okay? So what you will have, of course, you have here, no? If you have this initial primary alcohol, you expect to have an primary alkene. Dapat din niya. Okay? But what we actually obtain is not this alkene here, but you have your final alkene, which is more substituted one. Okay? This is how the rearrangement happens in a 1 degree alcohol or one primary alcohol. You get a more substituted alkene. Okay? So the rearrangement of the primary alcohol occurs via the E2 mechanism first here before if you get your final alkene. Okay, So first you have your primary alcohol again, and then after that, you have your dehydration process. You protonate this one, you protonate this, and you have your leaving group. And then you get your primary alkene here. Once you get your primary alkene, you actually do rearrangement. Okay, so protonation first to get your alkene. After you get your alkene, you do the rearrangement, no? Where the produced alkene becomes your base to obstruct the acid, and you get this one, carbocation, a more, you always have to choose a more substituted carbocation, then you get your final alkene. Okay, so the final product is this, okay, not this one. This is only produced in minor amount. Okay, so this is what happens to the 1 degree alcohol that do dehydration process. So now let's move on to the, I don't have time, the terminal alkynes. So okay, so for terminal alkynes, alkenes and alkanes, no, our alkynes are actually very acidic. Now, if you try to compare on the acidity of alkynes, alkenes, and alkanes, no, the pKa value of the alkynes are much very smaller than the alkanes. And for a terminal alkyne, it's 10 to the 20 times more acidic than alkene or alkene or alkane, actually. If you look at this, is a log value here. So it's 10 to the 20 times more acidic. So this proton here is acetylenic hydrogen is actually more acidic than those bonded to this. So this hydrogen is less acidic than this proton here. So this proton from the alkyne is very acidic compared to these two alkenes and alkynes. And since this one, the alkyne is much more acidic, so we expect their conjugate base to be, since this is the more acidic, so this expect its conjugate base. So this is conjugate base, the one with the lone pair minus the hydrogen. So you get the dot dot. This will become the least basic of the three. And then the next one is this one, CH2CH dot dot minus one hydrogen and an electron. This is the conjugate base of this. And then the last one, this is the most basic with the CH3, CH2 dot dot minus the sucker hydrogen, of course, the negative charge. So this is the most basic one. Their conjugate base, since this is the most acidic, its conjugate base is the least basic of all. And the relative acidity, if we try to compare our alkynes with other functional groups, with other organic groups, we've learned that the HOH, the water, the H from the water is much more acidic with a pKa of 15.7. And then the alcohol, next we have your alcohol, and then we have the acetylenic hydrogen from our alkyne, the terminal H of our alkynes. Okay, not the katong. Well, of course, we don't get a proton with daily terminal alkyne. So we only get your terminal proton, your proton from terminal alkyne to be more acidic here. And then this is actually more acidic than the proton from the amine, than the alkene or from an alkane. And we get the conjugate base of this. Okay, so since this is the most acidic, yung conjugate base niya ang the least basic, so that's the OH. We then convert this one to an electron dot. Okay, and this is the conjugate base, this is the least basic, and then you have the OR minus, OH minus, the least basic. And then the CR dot dot, this is actually more basic. The alkyne with its conjugate base with its electron pair negatively charged is more basic than the OR, than the OH. No, so of course we've learned that the OR minus is much more basic than the OH minus, but even the OR minus, it's less basic than this C triple dot C with an electron pair, and this is, we have the NH2 is much more basic than the OR, and of course the C triple bond C dot dot and CH2 dot dot is much more basic than NH2, and this most basic is the CH2 dot dot minus here. This one, the least acidic is the most basic. So you see this one is more basic. I just have to remember on the trend of the acidity and basicity of these groups. As we shall see soon, sodium amide is useful, especially when the reaction requires a very strong base. Explain why such a methanol cannot be used to carry out a reaction in which you might want to use sodium amide as a base. Why we cannot use a methanol as a solvent when we use the amide as a base? So the answer lies from here. Okay, so this is a very strong base. You have your pKa of your alcohol to be around 16 to 17, and you have, so this is a stronger acid, and this is a weaker base. And so to amide it's a stronger base, so it's conjugate. I mean, this is a stronger acid, and the ammonia is the weaker acid. So since it's a weaker acid, this conjugate base is a strong base, stronger base than this one. So the NH2, where you can have, this is NH2 dot is a conjugate base of the ammonia here, you see. So it can actually abstract this one here, okay, the H from the alcohol in such a way so the NH2 can actually abstract a proton from the alcohol to get your NH3 here. So this is a stronger acid and a stronger base, and of course you get a weaker base and a weaker acid. This is just what we've learned in Chem 139, the introduction part. So it matters knowing on the acid-base properties of our agents will actually is important, no, on what condition will the experiment have to go. So we cannot use the methanol when we are using NH2OH because this one is a stronger acid, and you have the amide as a stronger base, and they can do acid-base reaction where the amide can abstract the base. Okay, so you always have to choose a weaker acid, no, than the CH3OH. Okay, so weaker than this one, 16 to 17, for you to proceed the reaction. And this one is acid-base reaction that you've learned in Chem 130. You have to remember that if the equilibrium would not result in the formation of the appreciable amounts of product, you should so indicate. Predict the products of the acid-base reaction. So this is just similar to what you've learned in the previous Chem 130. No? So if you're not sure, you can look at the pKa of each. So with the protonated form, let's say compare the pKa of this and the pKa of its conjugate acid. So which one is a strong one? Which one would have a lower pKa? Okay, and that will be the stronger acid. And that will be the one to donate the proton, of course, in this. And you will have to predict the product. Would it be an appreciable amount or not? Same as this one. Okay.